Thank you, Jerry. Turn the mic on here. All right. Sound good for everyone? Awesome. Well, good morning, and thanks to Jerry and NCI for hosting me. I always really enjoy sharing the research that we're doing at Virginia Tech and at other universities related to metal buildings and cold form steel. So today I'm going to be sharing with you some new research and some new ideas. Well, they're not new now, but they're coming. They'll be new in the code soon, headed to you all in 2016. And so my goal today is to try to get you all pumped up about these new methods because I think they have really important benefits for the metal building industry. And this method is called the direct strength method. There have been many organizations involved in contributing to this, the development of the direct strength method over the years. And I should also mention that the presentation that I'm giving today, I'm recording, and so I'll have the voice plus the slides available to you all, however Jerry wants to provide it to you, maybe on YouTube or maybe his own. Jerry, do you have a YouTube channel? No, I don't. No? All right. So let's get going. The primary goal is, I know it's 7:30 in the morning, and I'm trying to get you all pumped up about the direct strength method, and I'm trying to turn you into believers of the direct strength method. So it offers a calculation-based alternative to things that you've been doing and the metal building industry has been evaluating with tests for a long time now. So I noticed many of you do not have your laptops. How many people have laptops here? All right, so I'm going to rely on you because for the first half of the presentation, I'll give you some of the background of the direct strength method. In the second half of the class, we're actually going to run through a metal building roof design example. And so right now, if you have a laptop and you don't have, for instance, UFSM, which is a finite strip elastic buckling program installed on your computer, you can get it here. I have a Z purlin file that I would like for you to download if you can, Z Houston. And there's an Excel spreadsheet, a DSM calculator that we're also going to use. And so I'll just leave these up here for a second so you all can make sure to grab these files. Oh, and happy Friday, by the way. Do you all have to get up this early every day for work? Yes? All right, did you at least get them written down so you can, all right, that's good, because I'm serious, I'm going to be doing this live, so I'm going to need some help in the last part of the presentation. All right, so the first thing is, what is DSM? So it's the direct strength method. So if you've all have used the effective width method in AISI S100, you realize that at least for flexural members, that the calculation is iterative. The effective portions of the stiff and unstiffened elements change based on the stresses and the effective areas within each element. Whereas the direct strength method, you have one number, you put it into the equations, you get the capacity. The design procedure is available for axial members and flexural members, and as I'll mention a little bit later, we've expanded it quite a bit over the last 5 or 6 years to start covering systems. So systems meaning, for instance, wall and roof systems in metal buildings. If you want to explore interesting cross-sections, if you have a wild cold form steel cross-section that you're interested in calculating the capacity of, now you have the ability to do that. And as I mentioned here, the big thing for me and for you today is to get you excited that you can actually calculate with equations and some software the behavior of a purlin or a girt in your wall or roof system. So you don't have to rely necessarily on the R factor method, or if you have, for instance, rigid insulation or insulation in between the panel, your through fastened panel, and then you can calculate that capacity of the girder purlin. So it's pretty exciting. So the direct strength method has, as I mentioned, has already been extended to cold form steel framing. So if you wanted to calculate the capacity of a stud connected to OSB or plywood, now you can do that. We've done some work on standing seam roofs, so we've demonstrated that this method can work. These are joists, but we could connect some cold form steel purlins as well, and we could calculate the capacity of a roof system with the direct strength method, and then what I'm going to be talking to you about today, focusing in on metal buildings. So the basic idea, and maybe you all have seen presentations by Professor Schaefer, who's pretty much the main driver behind the direct strength method, and who is really a passionate purveyor of the method. The way that we try to describe it is just through the physical behavior. So this is a column that I tested during my PhD, a C-section stud, and it's experiencing distortional buckling. So distortional buckling is where the flanges wave in and out along its length, and you may have seen that. It usually has a half wavelength of around 20 inches. More, it can vary depending upon the cross section, but for these SMA sections or C sections, it's about that length. And depending upon how susceptible your cross section is to distortional buckling, we have this strength curve. And you all are familiar with the column curve. So the column curve uses the Euler buckling load to calculate the capacity of a column. So if your Euler buckling load is really low, then your capacity of your column converges to that Euler buckling load. And so when we're thinking about cross-sectional instability, so that usually for the column curve, we're thinking global flexural buckling, Euler buckling. Now, when we start introducing thin-walled structures, we have cross-sectional instabilities. So we have a local buckling, so we have little half waves forming, or we have longer half waves like distortional buckling forming. And but we treat the capacity of that distortional buckling limit state or that local buckling limit state in a very similar way with the design curve. And on the x-axis is the slenderness, just the same way that you have KL over R for your global column slenderness, you have a slenderness for distortional buckling, the distortional buckling limit state or the local buckling limit state. And so if your column is very susceptible to distortional buckling, then you're down here. If your column or beam for that matter is not, then you're up here. So you can reach, this is the squash load. And so we have these elastic buckling parameters. So this is the Euler buckling load, but now we've just added two more. And now you can treat and calculate the capacity of thin-walled structures like these cold form steel studs, girts, purlins, whatever you'd like to calculate. So that's the basic idea. And I should mention that, so the column curve itself actually, so you see here that we're using PCRE, and so the AISC, which you're maybe more familiar with this KL over R, which was originally derived for flexural buckling, but in the cold form steel S100 code, you can find that if you play around with the limits of the column curve, you actually end up with this alternative equation or limit for global slenderness. And so I'm just showing you that even the KL over R is just a function of the Euler buckling load and the squash load. And so if you just play a little exercise in your mind here, so if you have PCRE is very small, that means that this ratio is very large and you're out here. And so that's the basic idea. So when in cold form steel we have other buckling modes besides flexural buckling, like flexural torsional buckling for singly symmetric sections, and so this is why we generalize this for cold form steel, but it's actually the same curve. Anyway, the DSM expression. So now I'm switching to beams, but it's a very similar idea. What we do is we look at the capacity of a flexural member now as the minimum of 3 limit states. So this is global buckling, which would be lateral torsional buckling for a beam. This is local buckling, and this is distortional buckling. We take the minimum, we say that's the capacity. these equations maybe are a little bit intimidating, but all we're doing here is, like, let's look at the distortional buckling equation. It's just my, which is, what do you think my is? I think you know that, right? It's the yield moment. And so, and what do you, if you had to guess, what do you think this number is? Do you think this number is greater than 1 or less than 1? It's got to be less than 1, right? Because we're saying that my is the maximum capacity that you can develop, but if you're susceptible to distortional buckling, then this factor becomes lower and lower. So you're just multiplying by my to get include the influence of distortional buckling on my. That's all it is. So if you look at these equations, don't freak out. Just like think of this number as less than 1, and you're reducing stuff you're reducing my based on a number. And I've already talked about this a little bit, but you'll see that, so for local buckling, you'll remember that you have to iterate for the effective width method. So you have to go, this is your procedure for the effective width method. You got like 20 steps at least or something. So the whole idea of an advantage of the direct strength method, if you get down to it, is that it's more accurate. So the effective width method assumes that each one of these, this plate, this is a simply supported plate, this is a simply supported plate, this is a simply supported plate, this is a plate that's supported on 3 sides, free on 1 side, and then you piece all those together. But they're actually all connected. And if you include all the connectivity, you can get something completely different. And so that's the advantage of the direct strength method. So we've demonstrated since 2001 that the direct strength method is more accurate than the effective width method in terms of strength prediction, in terms of strength prediction. And so more accurate means actually higher resistance factors for you all, which means like more efficiency. So this is a good thing for the industry. So let me just talk a little bit about, so let's just talk about a beam. So this is more academic here, but at least just trying to teach you to start thinking about how to deal with these different limit states, local, distortional, and global buckling. So you all have seen this maybe before. This is what lateral torsional buckling would look like in a beam, and so I'll show you the picture of it. So these are recent tests that we've conducted at Virginia Tech. So this is actually, if you had an unbraced C-section in uniform moment flexural buckling, this is what you would get. This is the kind of deformation you would get. This is the failure. This is the global buckling limit state for an unbraced cold form steel member. Then you have local buckling. And so we can pick up this local buckling in the program, CFSM, that I'm going to talk to you about in a little bit. This is just little half waves. So this is one long half wave. These are a bunch of little half waves, plate buckling. And this is what plate buckling looks like in a cold form steel joist. You can see the little half waves forming, and when these half waves form, you lose stiffness in the joist, and then when you lose stiffness in the joist, you get this failure mode. This is a typical local buckling, what we call a lens failure. So it's like a plastic yield mechanism, and this is how your joist would fail for local buckling. And then distortional buckling has these longer half waves. For a beam, it just happens on the compression side. And I didn't have a good picture without holes, but for sure, when you add holes to any kind of member, you increase its propensity for distortional buckling, and so because of the fact that the web is no longer bracing the flanges, and so you get these up-down half waves, and this is what distortional buckling looks like. And maybe this isn't a typical distortional buckling mode because most of the web is gone, but at least you see here that this is the type of failure that you would get where the lip buckles. And so these are the 3 limit states that you're after when you're calculating capacity in S100. All right, and so how do we get the parameters? So there's equations for calculating MC for lateral torsional buckling and flexural torsional buckling, flexural buckling, pi squared E over L squared, and then you have like the J's and CW's floating around in S100. So that's this part of the curve. um, here. But with a program called CFSM and with what we call finite strip analysis, we're able to characterize all of the buckling modes in one neat, nice little curve. So the x-axis on this curve is the buckling half wavelength. So so the buckling half wavelength is the distance between these half waves. So for local buckling, we have the little guys, and so local buckling occurs at something relatively short, maybe 4 or 5 inches, depending upon the cross section. Then we have another local minimum where we see distortional buckling occurring at a longer half wavelength, and then for global buckling, we have a long half wave here, which is, so we would pull that off whatever our unbraced length is for our beam. And so this is the basic idea. We have software you can plug this cross section in and get this curve. It's called an elastic buckling curve. So Greg Hancock from the University of Sydney coined it. I think he was the one who coined it the signature curve because it looks like a signature. Whatever you want, however you want to remember it. This is really, really powerful because it allows you to understand. If you wanted to, for instance, add a stiffener, change the cross section a little bit, you can study how each one of these parameters change, and each one of these minima change the influence the capacity of your member. We relate these minimum to the capacity of your member. And so this is the software that most people in North America and even around the world are using now. It's called CFSM, and it's pretty fun. The signature curve, as I mentioned, there's a couple. So Professor Schaefer's group is working quite hard to document the new version of CFSM. So you may have played around with earlier versions, but this one has some new powerful features where you can include fixed boundary conditions or other boundary conditions, not just simply supported. And so now we're actually going to watch this YouTube video now because I think you're getting maybe tired of listening to me, and so we'll have a little break here.
We do have internet access if you've got
So this is introducing the signature curve. This is Cara Peterman, who is a good friend of mine and a PhD student right now at Johns Hopkins University. If you listen carefully, you'll hear the sirens at the beginning of this video because you know that she's in downtown Baltimore.
Welcome to the CU-FSM 4 tutorial called The Signature Curve. CU-FSM 4 was developed by Professor Ben Schaefer and the Thin-Walled Structures group at Johns Hopkins University. This tutorial was developed by me, Cara Peterman, grad student at Johns Hopkins Civil Engineering. If you
Okay. So there are some other tutorials up there. There's actually, if you go to the COFSM page, there's PowerPoint tutorials, there's more videos, there's a bunch of stuff if you want to learn many of the details of the program. As I mentioned, it's very easy. For instance, if you wanted to play around with modifying your cross-section, you can put in these little stiffeners or bumps and see that, for example, for local buckling, so you have the critical elastic local buckling load used to be 1.03 times the squash load. Now it's 1.66 times the squash load. So you can see you can get significant benefits and find these benefits through optimization in this program. That's actually one of the most really powerful features of this program is optimization, and it's being used for that all around the world now to find the next generation of cross sections for light steel framing and even metal buildings. Well, why DSM? I think you get the idea. It's more general, it's easier, and as we're going to talk about now, there's system strength to be found by treating, so we can calculate looking at a member or a cross section, but bringing panel sheathing insulation to the design. I should also mention that DSM, so it started off with just beams with flexure and columns in 2001. Now we have shear calculations for beams. We have beams and columns with holes. We have sheathed walls, and this is the part that I'm working on, or have been working on for a few years now. As Jerry mentioned, we have a new steering group that's so a lot of the research is done, and what we're trying to do now is to start disseminating and convincing you all that it actually works. And so we have a steering group established through MBMA that's helping us to get through these final steps. And then built-up members, if you've ever tried to calculate a built-up section in S100, you have probably run into a brick wall, and so we're trying to remove that brick wall. Again with this method. So soon we'll have all of this encompassed, hopefully maybe by 2016. And as I mentioned before, 2016 is a big year for the S100 because of the fact that we're completely reorganizing it. For one, to follow more of the AISC organization. So you'll see here that there's quite a bit of quite a bit of similarity between the two, and something that's really exciting for you all should be this. Like I put this big smiley face here, because assemblies and systems, there's going to be a lot of potentially new information for you, for calculation-based methods that you can use when you're designing. So. And so now what I'm going to do is for the second half of the class, or second half of the class, sorry, I'm used to lecturing. I'm lecturing so much this week already. The second half of the presentation is to go through an example, a design example that you all may connect with. And this is a Z-section purlin with some 1 inch of rigid board and a through fastened panel. It's a 14 gauge, 8 inch deep purlin, 2 inch flange, steel yield stress 50. We're going to treat it as a simple span. Through fasteners are 12 inches and 1 inch is a Thermax rigid board. And so what we want to do is we want to calculate the capacity of this member for where this flange is in compression. We also have methods for uplift, but today we're going to go through the case where we have compression here. So before we get started, maybe let's just think a little bit about how this thing might behave. So what are the possible design concerns that we have for this type of roof system where we have insulation sandwiched in between? What do you think might happen?
The R factors aren't valid.
Well, yeah, that's one thing. That's right. But we don't have to worry about R factors because we can calculate the capacity now. Screw bending, for sure. What would be the, so would we would assume, what type of global boundary condition would we assume for this? How would we assume that it was braced? If we didn't have the insulation, what would you all do? Yeah, so I mean, I think if you had these at 12 inches on center, you'd probably assume that it was fully braced, right? Yeah, so you would just go and you would do the checks for local buckling and distortional buckling. And for this type of section, you probably don't have, maybe you don't have local buckling controlling. Distortional buckling, because of the fact that you're connected to the panel, you could maybe get away with that. And so you'd probably get close to the MY for the capacity, right? But so how do you think the rigid board insulation influences the three limit states then? So we have local, global, and distortional. How do you think? So is local buckling affected, do you think? So where is local buckling happening?
It might be affected slightly if you saw it.
Yeah,
You've got an additional sponge in there.
yeah.
Stiffness of the board, probably not much.
Probably not much, because this is all the local buckling is going to be happening here, probably. So distortional buckling, is that going to be affected? Yeah, it's definitely going to be affected, and it's most likely going to be suppressed most of the way. And then, so we have a 25-foot unbraced, or 25-foot span. So what is the lateral torsional buckling going to be affected by the insulation? It sure will. So you are probably not fully braced anymore, and so how would you take that into account? As what was your name? Bob. So Bob mentioned that you could put in some sort of spring and deal with it that way. And so what we can do in COFSM is, so not only can we treat members without anything connected, but we can put in springs anywhere we want and calculate the critical elastic buckling moments, including the rigid board insulation, including the panel, both rotational springs and translational springs. So that's what we're going to do now. Yeah, so well, that's a great question. So if we're doing nonlinear springs, then we're actually doing, we should be doing second order analysis, like in a structural analysis program. What we're doing is we're just calculating elastic buckling loads. And so we're calculating, so just like the Euler buckling load, but now we have some stuff attached to whatever we're doing. So that's a little bit different. And that's like, actually, honestly, that's the vision probably 15 years from now, like, yeah, 2026, 2030, when we're all still designing, right? You'll just run this, essentially a simulated experiment. So you'll just like have your system, you press go, and you'll just run the system to collapse and see what it looks like. There will probably, I mean, this is my vision, but design equations are going away. But we're not quite there yet. We're kind of in between. We're transitioning from yes. What about for what section? So for, we can deal with those. We can do it. Yeah, no problem. Actually, I'll talk about closed sections in the jam stuff. But all right, so the steps. Let me make sure that we have enough time here. All right, so the steps are here, and let's just get into it. This is what we're going to do. So we need a rotational spring and a translational spring that we're going to attach here, and we're going to calculate the elastic buckling moments, including this. So in our research that was funded by MBMA, we derived rotational springs based on a bunch of tests for rigid board insulation. So now we have an equation to calculate the rotational spring based on the yield strength of the foam. So there's different yield strengths. So Thermax versus, what are the other foams? I forgot. XPS or something? Like there are different yield stresses. And so different yield stresses provide different rotational and translational restraint. So you have to be careful with that. This is the equation that we came up with. It's just the yield stress of the foam, 2 times C squared. This is an academic term, but it's just half the flange width from the fastener to the corner of the cross section. And the units are a little bit tricky. If you calculate this out, it looks like force, but it's actually force times length. So it's moment per radian per length. So it's a stiffness, a rotational stiffness along the length of the member. Everyone get that? Kind of? All right, good. That's good. All right, so we can calculate rotational restraint including for when we have rigid board there. We can actually calculate rotational restraint when we have just the bare panel. We have equations for that now too. So that's going to be, you'll be seeing that in 2016 as well. All right, so this is our very fancy experiment to calculate the translational restraint. We put in a fastener, we pulled down, we measured the force that we pulled down with a scale, and it moved 53 newtons over 25 millimeters. This works out to not very much for a translational stiffness. Pretty much the fastener cuts right through the insulation. So this is 3 pounds per inch along the length. This is for a 12-inch fastener spacing. But this is still valuable. You will see here in a second when we put this in. You shouldn't throw this away. You can still get something out of it. And so we have those two springs, and we can put them in and calculate the capacity. So let's do that now. So you can see that pretty well, right? So at this point, if you have downloaded that Z Houston, you can open it. This is what it should look like. And we're going to put in some springs. So there's a thing down here at the bottom where you can input a spring. So we're going to put a spring at 27. The degree of freedom is x is 1. Here, let me turn on the coordinate system. Oops. It's not right. X is 1. Z is 2. It's in the x direction. It's a translational spring. We put in the spring value, which is 0.003. And the K flag is, I want to make sure I do this right. K flag indicates total stiffness or foundation stiffness. So we have a foundation stiffness. This is 1. Okay, so update plot. Oh, I forgot to connect to. My software will only run if I'm connected to the Virginia Tech network. There we go. So now see I have a little spring shown here. Now I'm going to put in a rotational spring. Oh, actually I need some help calculating the rotational. So if we can go back here, can someone calculate that? It's a 2-inch flange, so C is 1 inch. Actually, that's pretty easy. It's 1. I could even calculate that. How about that? 1 and then 2 times what? Okay, so this is another quiz here. Oh, I got out of my Sorry. Let me see here. There it is. So what's the yield stress of the foam? This is XPS. This is Thermax. What do you want to use? 22. All right. So and it was 2 times 22, right? Is what we decided. Was that the equation? I think so. The degree of freedom is theta. This time is a rotational spring 4. 40. Is this? We're putting in 44. Do you agree? Okay, good. Now we have a rotational spring there. So we have included the influence of the rigid board insulation in the model, and now we can go through what Kara explained earlier. We can go to the applied loads. Actually, first I think we have to go to boundary conditions. Boundary conditions, we're going to run the typical signature curve. Applied load. Put in 50. So this is cool also. So as I mentioned, beam columns is another thing that's coming for the direct strength method, and so you can combine different, you can combine any types of moments that you want on the cross section. Today we're just going to be dealing with a stress distribution like this. And if we're happy with that distribution, as Kara would say, we submit it. All right. And so now we're ready to analyze. So this is what the deformation will look like. Or this is what the elastic buckling modes will look like. So let's go take a look at the first minimum. Whoops. Oh boy. So what is, oh, I missed it by one, but. So what is this? What do you think is going on here? This is local buckling. So this is what we would call MCRL. We would grab this off. So those of you who have laptops, can you write that down? That MCRL is 1.38 times MY. And it's occurring at a half wavelength of 4 inches. And that's very typical. So for a flexural member, when you have a depth of 8 inches, the half wavelength will be half of the web depth. That makes sense. You'll have the bubbles occurring at 4. Then let's go to over here. Whoa. This isn't big. Not that happy here. So what do you think this is? This is so cool. I'm very excited for you to try to figure out what it is. It's lateral torsional buckling. So where did distortional buckling go? It went away. It went away because of the rotational spring. So it's not there. But something else that's super cool here is that, so usually for lateral torsional buckling, you have one long half wave, so that deforms along the full span, right? But when you add a spring, now it's like a column on an elastic foundation, and you can get multiple half waves even for lateral torsional buckling. So the half wavelength for lateral torsional buckling is 120 inches. So that's 10 feet. So how many half waves, how many lateral torsional buckling half waves will you have in your purlin? If our span is 25 feet. 2. So this is something else you have to realize, that lateral torsional buckling changes when you have these types of influences, like a lateral spring. And so if you're thinking about designing bracing or something, like if you want to try to solve it, then you have to realize that you have 2 half waves. And so if you put bracing in the middle or something, you're not going to do anything, right? It's going like this. So this also opens your eyes to things that you might not consider. So, all right, so MCRD is gone, infinity, you can set it to that. So infinity times MY, and MCRE is 1.03 times MY. So people got that? All right. And now let's just go and plug, actually I forgot to grab MY when I was looking over here, so hang on a second. Apply load. I'll put in 50 here. This is. You can, if you can, also write down that MY is 59 kip inches. All right, so now I think we're ready to roll here. We can just go to DSM calculator. So I've given you the link. That's my lecture schedule. That's at 10. Oh, I got a bunch of stuff open here. Let's see here. DSM calculator. There we go. This is a very simple spreadsheet. So we can type in, so MY was, oh, Jerry's got it right here. 59. 59, you want to do 59.3, Jerry?
Okay.
I'm getting feeling frisky today here. MCR. Oh, I need to make this bigger. I can't see anything here. All right, MCRL. Oh, we had that already. So MCRL, what was that? 1.338. MCRD is gone. And MCRE was 1.03, right? For lateral torsional buckling, right? That's it. So that's all. We just type in those four numbers. We have so we use these equations. We calculate MNE. So MNE is 48. So we see that there is some lateral torsional buckling influence, but it's not too bad. It's not fully braced, but we're close. 48 versus 59. The local buckling is the same as the global buckling. So what that means is that there's no influence from local buckling. I always struggle to try to explain this, but what we always do what's happening in this direct strength method, and actually what's happening in the effective width method as well, is you always start with the global buckling load, like the global buckling capacity or flexural torsional buckling capacity, MNE or PNE. And then if you have local buckling, then it reduces PNE or MNE. So that's what we call local global buckling interaction. So in this case, because MNE is equal to MNL, that means that that there's no local buckling influence. And that makes sense because we're using a 14-gauge purlin, which is pretty thick. If we had something thinner, then maybe it would be different. So in the end, we end up with the capacity of the member being 48 kip inches. And so it's actually not that bad. You don't take that bad of a hit from the rigid board insulation. And that's how you do it. Are there any questions? Yes. Yeah, I would just try to get close to where I was supposed to be, and I would put them at the quarter points of the span if I had rigid board. You just have to. That's for you guys to figure out. I'm just the academic. You'd have to take those brace forces somewhere. What'd you say? This force should be really small. The brace force should be really small. So I don't think it will hurt the Z section. It won't contribute significantly to the stresses. What was your name? Tom. Thanks, Tom. Any other questions?
So would you handle a pre-fastened panel in the same fashion?
You would, except the translational spring would be just a pin. It would be infinity. Like you put in a really high stiffness, or you could put in a pin in CFSM. The rotational spring still has a certain value that we have equations for, based on the thickness of the panel and the shape of the panel. Any other questions? Yeah, I mean, yeah, if you don't have the panel connected to anything, then it's just, then it should be, then it should be unbraced. Yes, yes. Or that, yeah. I mean, you have to use your discretion for sure.
You guys, with the MA program, looked at insulated metal panels, so now with fastener, I got a metal skin, then foam, and then another metal skin, so it's not good.
No, we haven't looked at that, but that's the idea. This is another great question. So that's the idea of this method, is that we have this framework, this tool, where you can plug in whatever you want. You just have to measure that. Like, we have a testing protocol. If you measure the stiffness, you can put it in here and you're ready to go.
I get you some insulated metal panels for cheap.
Unfortunately, students and university labs are not cheap, so. Tuition is going through the roof. I'm getting hammered on all my projects. Any other questions? Jerry, I'm almost finishing on time. How about that? 4 minutes early. And no other questions? Well, as I mentioned, I recorded the whole presentation. I'll post it somewhere so you all can see it. And we're really interested. We're at the stage now where we have most things worked out, and the last thing that we need to do is convince you all that this works, and to teach you how to use it. And then for sure there'll be, I think, really significant benefits for you all, for the industry. So, all right. Thank you very much. Sorry, let me just stop my recording here.